Alright, we're going to move on with our graphing unit. So our third lesson we'll start today is using derivatives. So in our first lesson, remember we would find our x and y intercepts. So we could make x equal to 0 to solve for y-intercept, make y equal to 0 to solve for x-intercepts, and that applies to any equation. And then on our last lesson, we looked at finding our asymptotes. So remember, for any kind of graph like a rational or a log, we could find vertical asymptotes, horizontal asymptotes, and then we use long division to find oblique. And remember, you'll only get either horizontal or oblique, you won't get both ever. So our next step now today is take what we already did, and now can we go one step further. So we're going to look to see what the first derivative of an equation will help. And if you look at the picture that I have on the title page, you can kind of see what's going on. So remember, our first derivative gives us slope. So it's not necessarily that we have to actually calculate what the slope is, but if we can calculate whether the slope is positive or negative. So you can see on this picture, this tangent line at point C is a positive slope, and that's, or we'd say the slope is increasing. At point D, we can see it's a negative slope, or decreasing. So then what's happening at point A? Well, at point A, the slope is changing from positive to negative, or at that location the tangent line would have a slope of 0. So we can take the slope values and see where they change from positive to negative, or down in the bottom here we can see it's going from negative to positive. Wherever it changes is going to tell us where the slope is 0, which will also tell us where the maximums and minimums are. So that's the new wrinkle that we're going to add to today's stuff. So to start with, let's look at a basic equation. So we know from quadratics what the general shape is, and we can find some of the key information. So let's do a little bit of review of everything we've done so far. So with this quadratic, we could figure out our y-intercept by plugging in an x of 0. So we make x 0, that would give us negative 5. And if we make y 0, we can find our x-intercept, or intercepts if there's more than one. So in this case, if we factor the right-hand side, we would get minus 5 and plus 1. So in this case, we should have two x-intercepts at positive 5 and negative 1. And we could write those as a coordinate if we want as well. So we have two x-intercepts, one y-intercept. So from a graphing perspective, we have quite a bit of information. So we can plot those points. Let's put our negative 5 down here somewhere. Positive 5 would be about there, and negative 1 about there. So just by eyeballing this graph, we can see our quadratic should do, something like that. It's a little bit crooked, but good enough. Okay, so we have our quadratic that would go through those 3 points. What we don't know is how far down does the quadratic go. So this minimum on this graph, where is it located? So this is where our first derivative should help us out. So if we go back to our equation and we do the derivative of that equation, we'd get 2x minus 4, just regular power rule. So if we look at certain locations, so if I put in an x of, say, negative 3, and you plug negative 3 in there, that gives us negative 10 for a slope. If I put in x of 0, that gives us negative 4, so that's a negative slope. If I put in an x of 2, we get 0. So that's going to be our key point. So what we're going to do is we're going to actually do the derivatives, and then we're going to make the derivative equal to 0, and that'll tell us where our graph is changing from positive to negative, or from negative to positive. So if we take that equation and solve it now, we can see that we would get x equals 2. So what we have going on then is we know that this location on the graph is at 2. So you can see just the way I sketched it, everything on that graph below 2, so from negative infinity to 2, is going to be a negative slope. Oops, I got that backwards. That'll be this bottom one. And then where the graph is rising would be where the slope is positive, so that'll be everything bigger than 2. So it'll go from positive 2 up to infinity. So we've kind of broken the graph into those two intervals. So then at 2 will be the only location where our slope would be 0. So that minimum is then located at 2. So the only thing we have to figure out is what is the y-coordinate of that minimum. So we know the x is located at 2. So to get any kind of y-coordinate, always go back to the original graph. So we plug 2 into the original, we would get 4, minus 8 minus 5 would give us negative 9. So this graph, the way I got it drawn, that minimum location should be at negative 9. So if we took, let me erase my blue line here. So if we get rid of our curve, we still have our x and y intercepts labeled there. So our x-intercept was at negative 5, so let me make that a little bit more realistic. So negative 9 now will be quite a bit lower. And we know it's at 2, so it'll be somewhere down there. So there's our 2, negative 9 coordinate. So now having that minimum will actually give us a way more accurate graph. We'll know how far down it goes, plus we'll know those x and y intercepts that it crosses at. So for most graphs, the maximums and minimums, if they exist, will definitely be of use to help figure out. So what we're basically doing is we're taking any kind of equation, doesn't matter what it is, we're going to look at the first derivative. So we're going to take that first derivative, and what we're going to try to figure out is where that derivative is equal to 0, and then we're going to test either side of those locations to try to figure out whether they're negative or positive. Because we don't know which type it is. So if I told you, like for this last question, we knew we had a minimum at 2, but let's suppose we didn't know it was a minimum or maximum. So if we know that we got something happening at 2, and if we test on the left side and it's positive slope, and we test on the right side and it has a negative slope, so we would just plug whatever those coordinates are into our first derivative equation. So if I plugged a 0 into this equation and we got a positive number, well, that would tell us everything left of 2 is positive. If I plugged a 3 in and we got a negative number, well, that means everything right of 2 that's bigger than 2 would then be a negative slope. So then just by analyzing that, a positive slope goes upwards, a negative slope goes downwards. So that means at 2, we're switching from an increasing or positive slope to a decreasing negative slope. So that'll tell us that we have to have a maximum at that location. If at negative or at positive 2, it was the other way around. If we had a negative slope on the left and a positive slope on the right, now our graph would go the other way around. So that would tell us we have a minimum slope. And if we had a situation where it didn't change, so let's suppose we had a positive on both sides, well, we don't have a maximum or a minimum. And in this case, we're going to do more of these later on, but in this case, it would be kind of a graph that does something like that, where it just switches, makes like a little S-curve type of shape. But we'll deal with those later on. So for today, we're just going to try to figure out if it's a max or a minimum and what is the coordinate of that location. So let's do another example, and let's do all the parts of it. Let's try to figure out if we can solve for everything, not just the max or mins. So I've got on here, let's find where the interval is increasing or decreasing. But like I said, let's do more than that. Let's actually solve for everything. So the first thing we want to do is, let's start with our x and y intercepts. So let's do our y-intercept first. So that's an easy one. Plug a 0 into the equation, we would get a y-intercept of 2. Okay, x-intercepts are going to be where that equation is equal to 0. And it's a cubic equation, so that means we'd have to do long division, synthetic division, and then hopefully we'd get nice numbers. So in this case, like -2 or something like that probably works. But for a lot of these questions, you're going to get decimal intercepts. So the best bet is just to graph it. So you can just graph this like you normally would. And it'll help you to see what the shape looks like, so then you'll know you're on the right track anyway when you go to do the graph later on anyway. So let's put this on our calculator and graph it, so we can see what kind of cubic graph it is. So it looks like a normal cubic. It's got 3 x-intercepts. So I'm just from the calculator, I'm going to determine the x-intercepts. So we have our first one, looks like it's a decimal. Looks like it's what, -3.7 or something like that. So I'm just going to use the calculator to solve for it quick. Oh, it gave me the bigger one first. That's okay. I'll do them in highest first. So our first one's at -0.27 approximately. The next one is at -2 exactly. And our third one looks like -3 point something. So my calculator is giving me negative 3.73. Okay, so for these, algebraically, we don't need to show our work for x-intercepts because you did that in Math 30 and it's kind of beyond our point of the course here. So we've got our x and y intercepts, which will help us draw the graph for sure. But again, we want to figure out where those max and mins are. So more importantly, let's do our first derivative. So we take our original equation, do the derivative of it, so that would give us 3x squared plus 12x plus 9. We're going to take that equation, make it equal to 0. So let's factor out a 3 as well to make it a little bit easier. We're going to make it equal to 0. And let's factor the inside parts. We get plus 3 and plus 1. And we can see that our two critical points are going to be at negative 3 and negative 1. So what we don't know is which one's a max, which one's a min. So this is where the next part's important. So when I wrote on here to find the intervals where it's increasing or decreasing, what that's going to tell us is whether it's a maximum or a minimum, or neither. So let's do some test points. So we have our first derivative equation. That's going to tell us the slope. So what we want to do is determine what the slope is doing on either side of these equations. So if we test a negative 4, we're going to plug a negative 4 into that equation and see what happens. So if we put a negative 4 in there, you'd have 3 times 16 plus 12 times negative 4 plus 9. So that gives us a pretty big number, so it's going to end up being positive whatever. And again, we don't really care what the number is, we just want to know whether it's positive or negative. So now let's try a negative 2. So a negative 2 somewhere in the middle. Plug negative 2 in there, that gives us 3 times 4, which is 12. Take away 24 plus 9, which will end up being a negative number. So we can see that we're switching from positive to a negative slope. So we know then at negative 3, it's going to be a maximum. So that definitely helps out. So we have a maximum at negative 3. And then let's test past negative 1. Let's try 0. So if we plug 0 into this equation, we get 9. So we're back to positive again. So you can see then switching from at the negative 1 location, we have negative slope changing to a positive slope. So we would have a minimum located at negative 1. So that should be it. We've got pretty much all of our key information. So we have our x-intercepts, we have our y-intercepts. We just determined that we have a maximum at negative 3. So let's put that down on our list here. So we have a max at negative 3. We'll determine the y-intercept in a minute. And then we also have a minimum at negative 1. So to figure out the y-coordinates, always go back to the original equation. So if we plug negative 3 into that equation, we get positive 2. And if we plug negative 1 into that equation, we get negative 2. So that's it. So all of this information that we have at the top in black should be everything that we need to draw the graph. So let's try it. So if we look at our graph, we have a y-intercept at 2. We have 3 x-intercepts. One is at negative 2. One was at 3.7, so I'll do it a little bit less than 4. And the other one is just a little bit bigger than the 0, so something like that looks good enough. We just figured out our maximum is at negative 3, 2. And we just figured out our minimum is at 1, negative 2, something like that. So just from all of that, we've got a pretty good idea of what this graph's going to look like. It's going to go up to that maximum, down to the minimum, and then back up again. So that should be our final function for this. So not only do we have x, y intercepts, these max and mins tell us how big these curves are, because we really had no idea if the graph did that, or maybe it went way taller. You know, it could have looked something like that, or it could have been shorter, whatever. So the graphs can change depending on where those max and mins are located. So to recap, the most important step is solve your equation equal to 0, your first derivative equation equal to 0. That'll give you the locations of where the max and mins could be. Then what we want to do is we want to test on either side of those intervals. So we tried a negative 4, and that gave us a positive slope. We tried a negative 2, which gave us a negative slope. Then we tried a 0, which gave us positive again. So again, that told us then our negative 3 was our minimum. and then we plugged in that into our original equation to get the y coordinate, and then we saw that our, oops, I did that backwards, sorry. We had positive slope to negative slope, so the -3 was our maximum, and then the -1 was the other way around, went negative to positive, so that gave us the minimum location. And that one was at -1, -2, if I recall from the previous page. So we can find where they are, plug them into the original, we'll get the coordinates, but then we still need to do the testing to figure out whether it is a max or a min or neither. That, we plug all that key information, so this is just a better graph of what we just did. So there was our max and mins, we had our x and y intercepts from before, connect all those dots, that gives us our graph. Okay, so let's try another one. So here's a 4th degree, and if you remember from Math 30, 4th degree equations could be a W shape like that, where we have 4 x-intercepts. Maybe it only has 2, and the other ones are up higher. Maybe it doesn't have any. Right? It could be any of those scenarios. So without using our calculator, it's going to be quite tough to figure out which scenario we got going on. So this is where it'll be good to use the calculus to help you figure it out. So once again, let's go through all of the different steps. So let's do our x and y intercepts again. So this one, the y-intercept is easy. It's at 7, but the x-intercepts will be a bit tougher. But again, we can just use our calculator to help us out if we need to. So our y-intercept is at 0, 7. X-intercepts we could have up to 4. But if we graph them, let's plug it in our calculator quick to see what we get. So we have x to the 4th plus 4x cubed plus 7. And we graph that. So it looks like the graph only has 2 x-intercepts. The other 2 are above, and it looks like it makes like a little S-curve. So just by looking at my calculator screen, it's doing something like this. Okay, which is still a 4th degree, but it's kind of a weird one. So let's see if our calculator ends up matching that picture. So our 0, 7 we already figured out. So that's our y-intercepts. We've got that accurate. So let's figure out our x-intercepts. So from our calculator, let's just calculate because they look like they're decimals. We're getting negative 1.39. So that's this first one is at negative 1.39, and the second one looks like it's almost negative 4. So we'll find that one as well. I got negative 3.88, so that looks good. So we've got our 2 x-intercepts. Like I said, it's almost at negative 4 and negative 1, but close enough the way I sketched it out. So we've got our x and y intercepts. So now by looking at this graph, we can see that we definitely have a minimum. So let's do our first derivative. So that gives us 4x cubed plus 12x squared. Let's make that equal to 0, and let's factor out a 4x squared to make it easier. So we just get x plus 3. So if we solve each of those, we get 0 and negative 3. So again, it's important to do our test points to see what's happening with our slopes. So let's go from left to right. So let's try a negative 4. So we remember we want to put negative 4 into our derivative equation. So that'll give us a pretty big negative number because it's going to be like negative 64 plus whatever. So that'll be a negative value. Let's try negative 1. That's a pretty simple one. So at negative 1 into that equation would give us negative 4 plus 12. So that'll be a positive value. And let's try positive 1. Put positive 1 into there. We get 16. So that's also positive. So you can see from our testing now we have a negative slope here turning to positive slope. So we definitely have a minimum at negative 3. Let's make our little list on the side here. We'll figure out the y-coordinate in a second. And you can see at 0, it's going from positive to positive. So that means our graph was positive, it flattens out, and then it goes positive again. So this isn't a min or max, it's going to be an inflection point, and we'll talk about that later. But you can see on my picture, that's where that little S-curve is happening at the y-intercept. So in this case, we just have the 1 minimum. So let's figure out our y-coordinate, plug that back into the original equation, and it gives us negative 20. So this minimum on this graph is way down at negative 20. And that's it. So even though it's a 4th degree, we still only had the 2 x-intercepts, the 1 minimum, and the 1 y-intercept. And from that, we could get a pretty good idea what the graph is going to look like. So if you remember with all of that graphs, if you have something like just y equals 1 over x, remember that graph looks something like this. So a basic rational graph has asymptote lines, but it doesn't have max or mins. But if we do a graph that has a oblique asymptote line, so let me just estimate, let's suppose it did something like that, and let's suppose we still had a vertical. This one, our curves end up being kind of 2 quadratics tilted sort of like that. These ones will have max and mins. So depending on the function, we may or may not need to calculate the max or mins. So the key one to worry about is if there's oblique, it will have max or mins. If it has horizontal asymptotes, then it won't. That's generally the way to keep it separated. So the last question I have for you, this one's very similar, once again. It's rational graph. All of our, so we have instead of our polynomial one, let's plug in an x of 0, the rational stuff. So we have our y, and if you remember, y-intercept 3, let's go to x-intercept. Calculate our x-intercepts. Oops, I lost one equation. Our x-intercept equal to 0, so my equation went away, so let me rewrite it on here. So we have x squared plus 3 divided by x plus 1. So remember with x-intercepts, it's only the top, because once we plug in a 0 for y, we would multiply the bottom out anyway, so that goes away. So you just get x squared plus 3 equal to 0. So in this case, let me just write the final equation down here. We would bring the 3 to the other side, so we'd have x squared equals negative 3, and then when we square root both sides, we can see that you can't get a square root of a negative number. So in this case, we have no x-intercepts. We don't have to worry about the x-intercepts at all. So the only thing we've got to figure out is our asymptotes and then our max and mins. So let's go through the asymptotes in order again. So vertical asymptote, remember, is from the bottom value. So that'll be at negative 1 in this case, right? What makes the bottom equal to 0. Horizontal asymptote, we would divide our highest powers. So we'd have 1x squared divided by 0x squared. Well, once again, can't divide by 0, so that means we have no horizontals. So we should have an oblique. So with oblique asymptotes, remember we need to do long division. So let's do that up over here in the corner. So if we divide out our equation with long division, remember you want to divide the first two numbers, x squared divided by x, which would give us x. Foil that out, so x times x is x squared, x times 1 is 3x, or 1x, sorry, and then we still have the plus 3 at the end, so let's just carry that down. So we need to subtract these, so if we're subtracting all of this stuff, I guess we didn't need the 3 just yet, but if we subtract all of that stuff, you'd have x squared minus x squared, which cancels, but we also have a 0x in here, so 0x minus x would give us negative 1x. Then we can bring down the 3 if we want, but remember we don't really need that for oblique, we just have to do the divisions twice. So x squared divided by x gave us x, now we need to do it again, but we would use our remainder, negative x, and we want to divide by x plus 1 again, so we're only dividing those front terms. So negative x over x would give us negative 1. And that should be it for our oblique equation. So we've got y equals x minus 1, should be our correct oblique asymptote line. So we've got our intercepts, we've got our asymptotes, so our last thing to try to figure out would be our max and mins. So let's go back to our original equation again, and in order to calculate max and mins, remember we need to do our first derivative. So I would do this as a quotient rule. So let's call our top term the x squared plus 3. So that derivative would be 2x. Our bottom term is x plus 1. So that derivative is 1. So when we do our product rule, let's write it over here. So our product rule will be 2x times x plus 1. And then we would subtract the 1, that's equal to 1. So we'd have 1 times x squared plus 3. And that would be all over our bottom term squared. So let's simplify the top and see where we can go with this. So our top would simplify to 2x squared plus 2x minus 1x squared minus 3 all over the bottom squared still. And let's clean up the top a little bit more. So we'd have 2x squared minus 1x squared, which would just give us 1x squared plus 2x minus 3. Bottom stays the same. So our last thing is now we want to make that derivative equal to 0. So again, we only worry about the top. So we want to take that top equation, x squared plus 2x minus 3, make that equal to 0. So let's factor it. So we get minus 3 and plus 1. Oops, the other way around, plus 3 and minus 1. And so our two solutions should be negative 3 and positive 1. So the only thing we don't know what that is are those maxes or mins. So again, let's go back to our number line and let's test. So let's try plugging in a 0, right? 0 somewhere in the middle. So if we plug 0 back into our first derivative equation, let's use this version as the simplest. So plug 0 into that, we'd get negative 3 on the top, 1 on the bottom. So that's going to be a negative slope. Let's try a positive 2. So we plug a 2 in, that would give us 4 plus 4 minus 3, so that's 5 on the top, and we would get 9 on the bottom. So that would be a positive. And if we plug in a negative 4, that would give us 16 minus 8 minus 3, so that'll be positive on the top, positive on the bottom. So we're back to positive. So we can see then positive slope changing to negative slope. We got a max at negative 3. Negative slope changing to positive slope. We're going to have a minimum at positive 1. So let's put that on our list over here on the side. So maximum at negative 3 something, and our minimum would be at positive 1. So all we got left to do is figure out those y coordinates, and we're done. So our y coordinates, we're going to go back, let me clear off the screen here a little bit. We're going to go back to our original equation. Oops. So we're going to take those original numbers and put them in those max and min numbers into our original equation and see what happens. So I'll just make a bit of room here so I can draw the graph. So we put in a negative 3 on the top, so negative 3 squared is 9, plus 3 would give us 6, divided by negative 2 on the bottom, so that would give us 12 on the top divided by negative 2. So that'll give us negative 2 for our maximum coordinate. And if we plug in a 1, that gives us 4 divided by 2, which would give us positive 2. And that's it. We should have enough to sketch out our graph now. So let's go through all of our key things. So let's start with our asymptote lines. We have a vertical asymptote at negative 1. So it should look something like that. Our oblique was y equals x minus 1. So that'd be something like that. So there's our two asymptote lines, and again, let's label these. These are at minus 1. This will be at positive 1. That'll be at minus 1. And we had a y-intercept at 3. Let's label that. And we had a max. Let's do the minimum. Minimum was at 1, 2. So that's about there somewhere. And we had a maximum at negative 3, negative 2. So I'm off a little bit, but let's cheat a little bit. Let's just move my negative 2 down a bit, so it'll be somewhere down here. Okay, And that's it. We've got everything figured out. So you can see our curve then will go between these asymptote lines, through the y-intercept and through the minimum, something like that. And then our one on the bottom will just go through that maximum, and it would look something like that. So my graphs are a bit off, but you get the idea. So that's it. So our first derivative will tell us where the slope, what the slopes are. We figure out where those slopes are equal to 0. That'll tell us where the max or mins are. We use our little test points to determine which one it is. And that'll be it for today. Tomorrow we'll move on to a little bit more with max and mins.